What is up, everybody? Welcome back to another reinforcement learning tutorial in the OpenAI Gym. In this episode, you're going to learn how to go from nothing to a fully implemented SARSA algorithm using only Numpy, Matplotlib, and Gym. If you've ever struggled with reinforcement learning, if you've ever wanted to get started with reinforcement learning, you are in the right place. Let's get started. So I have a pretty set process for solving reinforcement learning problems. So step 0 is to go to the documentation and see what you're working with for the environment. In this case, we're going to be dealing with the Acrobat V1, which is an environment from the OpenAI Gym. It's a classical control problem where you have a basically double jointed pendulum that is trying to swing into the vertical position. You can see here a random agent attempting to move vertically. It doesn't quite get there because, well, it's a random agent. So first thing we notice right away is that the documentation here is incredibly sparse. We don't know anything about the environment. So step 1 then is to click on View Source on GitHub. And let's see if we scroll down. Okay, take a look at the description of our class and see what we see. So here it says, Acrobat is a tooling pendulum, blah, 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 blah. State. The state consists of the sine and cosine of the two rotational joint angles and the two joint angular velocities. So it tells you that right here. So we have a 6-component vector. The first 4 components are sine and cosine terms of theta 1, theta 2 respectively. And the final 2 are theta 1 dot, theta 2 dot. Okay, cool. So what do we know from this? We know that the theta 1 and theta 2 cosine terms and sine terms are going to be bound by plus and minus 1. That'll be important later. We don't know anything about theta 1 dot or theta 2 dot. Okay, fine, we'll figure that out as we go along. The other thing we can read is actions. The action is either applying plus 1, 0, or minus 1 torque on the joint between the two pendulum links. Now stick this in the back of your noodle because it's a lie. It's not true. So this is the danger of reading the documentation, is sometimes you will get inaccurate or misleading information. This isn't done purposely. It's just an oversight. It happens, but we're going to figure out how to deal with it on our own. So let's go ahead and get into the editor and start writing some code here. Okay, so we took a look at the documentation. We saw that we have an observation vector of 6 components, 4 of them being sine and cosine terms. That tells us that they are bounded by plus and minus 1. The other 2 are velocities. We don't know anything about that. We'll have to figure that out as we go along. So step 0, make sure you have all of the required libraries. In this case, you're going to need Gym, Numpy, and Matplotlib. Make sure you have all those installed. Oh, also we'll need Pickle to save our model in case you want to save it and then pick up training later, or to do a separate training and testing phase to see how well the agent generalizes after the training phase. So the first thing we have to address is our state space is continuous. Now SARSA is a tabular learning method, meaning it literally makes a table of state and action pairs, and it tries to guess the value of each of those state and action pairs. It does that by sampling the by sampling transitions from the environment, taking actions, receiving rewards, and updating its estimates for the state action estimate. So we cannot use a continuous state space. So that is a problem right away. So we have to solve that problem by taking our continuous state space and breaking it into a set of discrete chunks. That's step number 1. And then we're going to have to figure out what the limits on the velocities are, because we have to have a finite limit on either end, positive or negative velocity, and the documentation doesn't tell us that, so we have to figure that out from experience. So let's start with that. So we want Gym and Numpy. We want to load up our main program, and the first step is to make our environment. That is Acrobat V1. We want to reset our environment. Actually, let's do this. Let's go ahead and loop for I in range 10. So we'll play 10 games, resetting the environment at the top of each episode. Reset the done flag, and then play the episode. So while not done, we want to take some action. So as I told you before, to stick this in the back of your noodle, the action space is supposedly minus 1, 0, or 1, so let's test that. Let's say action equals env dot action space dot sample. Now this is a function in the OpenAI gym that allows you to take a random sample of the action space. So for giggles, let's print the observation, let's print the action, and then let's take that action. Let's go to the terminal and run that and see what we get. Okay, so here we are in the terminal. Let's run the Acrobat, and we get a big output dump. So what do we see? Okay, we see an action of 2. Well, all right, fine. We know right away that we can have an action of 2 which directly contradicts the documentation. So what we see is action 0, action 1, action 2. Let's scroll. Do we see a 3, a 4, anything like that? Nope, just 0s, 1s, and 2s. Okay. Fair enough. So the documentation was off by 1. Instead of -1, 0, or +1, we have 0, 1, and 2. Not a big deal. What else do we observe? We see these observation vectors. So the first 4 are the sine and cosine terms. If we scroll up and down, we do see they are indeed bound by +, or -1. We don't see anything outside of that range, as you would expect from basic trigonometry, right? Next question is, what about the limits for the theta? So that's the final 2 parameters, and already we can see a 3.73, a 4.57, so it looks like 5 is a pretty good limit on the upper end, minus 3.38, okay. Scrolling down, we see lots of 1s, -1s, 2s, 3s. Do we see anything outside of the range plus or minus, say, 5? Scrolling, I don't see anything outside of the range plus or minus 5. Okay, fine. So let's say we can bound theta by plus or minus 5. And anything that falls outside of that range will get placed in either bucket 10 or 0 respectively. So this is how you find out state and action spaces for environments when you don't know anything. You just randomly sample them. Or if you had to, you could guess and say take some action that I guess and then observe the output. Okay, let's go back to our code and proceed. Alright, so here we have the makings of a program. So the next step that we want to take is to go ahead and take those continuous action spaces and turn them into something discrete. So we need a function to do that. We'll call that getState. That'll take an observation as input. And so we know that the observation is a tuple, right? It's or an array rather, a list. So we'll call it cosine theta 1, sine theta 1, cosine theta 2, sine theta 2, and then theta 1 dot theta 2, 2 dot equals observation. So this will unpack the list into 6 separate variables. So what do we want to do? We want to take those 6 separate variables and take them from a continuous variable to a discrete variable. So to do that, we have to create what are called spaces. Let's make these global variables just for giggles. So theta space, not just for giggles, so we don't have to redo it every single time we call the function. Numpy.linspace, so -1 to 1 with 10 bins. So what this will do is create a linear space between -1 and +1 with 10 buckets. So we need a theta dot space, and that's numpy linspace, call it -5 to 5 with a range of 10. So then the task then is to take the continuous variable and find out which bucket it falls into with each of those particular variables. So I shorten this here and say c theta 1 equals int. The reason we want to cast it to an int is because it returns a numpy number, or I think a numpy array. Let's just make sure it's an integer. And the inverse function is called digitize. So we'll take cosine theta 1 and see where it falls in the theta space. So then we have a sine theta 1. That takes a sine theta 1 space. We have a cosine theta 2. That takes the same old theta space. And we have a sine of theta 2 that does the same thing. Now we have velocities. So you have theta 1 dot, we'll say theta 1 dot equals int digitize we called it theta 1 dot and theta dot space. Do the same thing for theta 2. Boom. And so that is all you need to do to take a continuous set of observations and make them into a set of discrete observations. So one important question to ask is, how many states will we have exactly? So we have 1, 2, 3, 4, 5, 6 variables, right? So that means you have 10 times 10 times 10, right? 6 times. So you have 10 to the 6 or a million possible state combinations. And then you also have actions on top of that. So a fair number of combinations. Not too large though. So then we want to return c theta 1 sine theta 1, cosine theta 2, sine theta 2, theta 1 dot, theta 2 dot, and that should be a tuple. Perfect. So that is that. So the next step we have to take into account is the SARSA operation itself. So if you want to know how to do that, the best place to do that, to find that out, is in the textbook Sutton and Bartow, which is a wonderful reference. I referenced that in my video, How to Learn AI for Free. It's a free document that teaches you the ins and outs of reinforcement learning. So let's go ahead and take a look at that and see what it says about SARSA. So here we have the textbook. This is by Sutton and Bartow. It is the preeminent book on the topic. So we're going to implement SARSA. And so what's important is this shaded algorithm here. And so what do we see? We see initialize Q of SA for all states and actions in your state space arbitrarily and set Q terminal state equals 0. So we're just going to take that whole shebang of state and action pairs and set all those Q SA estimates to 0. So we're going to want to loop over some number of episodes, which we already have. Initialize the state, already got that. Choose action A from S, meaning choose an action based on whatever state you start in, using policy derived from Q. In other words, an epsilon greedy strategy. Epsilon greedy just means that some percentage of the time you pick a random action, and the majority of the time you pick a greedy action, which is the best known action given you're in some state. So that action selection takes place before the start of the episode, and then you want to repeat for each step of the episode. So take that action, observe your reward and new state, choose another action using your policy derived from Q, e.g. epsilon greedy, and then go ahead and use that action to update your estimate of Q using this equation. The QSA equals QSA plus alpha, learning rate, times the quantity R plus gamma, Q of S and A prime, which is your new state in action, where the A prime is the optimal action, minus QSA, and then set state to state prime and action to action prime. So that means you're going to take that action prime at the top of the next step, and do that until you finish the game. So we have to implement that algorithm. So that is pretty straightforward. Let's head back to our code editor and do that now. Okay, so we saw from the book that we need to have a way of selecting a maximum action. Now Numpy doesn't quite give us what we want, so we're going to write our own function to do that. So we're going to call that max action, and that will take the Q estimate, state, and a set of discrete actions, which we already know to be 0, 1, or 2. What we want to do is create a Numpy array of values Q of state and action for each action in actions. Then we want to find the argmax of that. And the position will correspond to the action because of the way we have this indexed, meaning 0, 1, or 2 position will correspond to action 0, 1, or 2. So we just return that. So now we have our way of selecting the max action. Next thing we need is to set up our hyperparameters. So looking back at the book, remembering back to the book, we saw that we needed a gamma and an alpha. So we'll also need a number of games, let's say 50,000. We'll need an alpha, that's the step size parameter, 0.1. It's a learning rate, if you're familiar with machine learning. A gamma, that tells us how much to discount each future reward. So 0 would mean that the agent only takes into account the present reward. 1 means the agent takes into account all future rewards, all past rewards, sorry. And then the gamma means, 0.99 means it's almost completely far-sighted. And then we need our epsilon greedy parameters. So we'll call the epsilon, set it to 0. So next thing we have to do is create and initialize our queues. So we need an action space. And we need to construct our state space. So we're going to brute force this because brute force always works, and if it doesn't, you're not using enough. For cosine 1 in range 11, so we have 10 buckets, right, for our spaces. So that means we need to use range 11. For S1 in range 11, for C2 in range 11, S2 in range 11, for, what do I want to call this, dot 1 in range 11, dot 2 in range 11. States C1, S1, C2, S2, dot 1, dot 2. But we have to make this tuples, and the reason is that we're going to represent Q by a dictionary. And dictionaries must have immutable keys. Lists are not immutable, however, tuples are, so fun fact for you. So then we need to initialize our Q table. For state in states, for action in action space. Q, S, good grief, state action equals 0. So this will automatically set all of the state action estimates for every single state action pair to 0, including our terminal state and action pair, which is precisely what we want. So next up, we have to iterate over our number of games, which we called n games. N games, and then we have to actually play those episodes. So let's say we want to know where we are. If I modulus, well, let's say 1000 equals 0, print episode I score, score, we'll define these in a moment. And let's go ahead and print the epsilon, because we are going to decrease epsilon over time. I take it back. Epsilon starts at 1 and goes down to 0. I spaced out for a second, sorry. So next step is to print that, and we have already reset our environment. So we have to create a score variable, set it to 0 there, and at the top of every episode we'll want to set it to 0 also. And so we have our state, right, obs. So now we have to say state equals get state obs, action equals max action q state. What parameters do we take? Q state, and we don't need to pass in actions because that's a default. If mp.random.random less than eps else env dot action space dot sample. Yeah, that's readable. So what this will do is it will take a random, it'll take the maximum action. Let's flip this. If it's greater than, otherwise it'll take a random action. So setting epsilon equal to 1 to start means that the agent will take entirely random actions at the beginning, and as we decrease epsilon over time, it'll start to take more and more greedy actions. So next thing we want to do is, let's call it obs underscore. Let's do it the easy way. Reward done and info equals env dot step action. Then we need to get our new state, and we need to get a new action. like so. Except we don't want to call that action. We want to call it action underscore. And then we want to update our Q function. And we can also keep track of our reward and update our Q function. State action equals Q state action. If I could learn to type, that would be really handy. Alpha times reward plus gamma times Q state underscore action underscore minus Q state action. Then set state to the new state and action to the new action. So this is the SARSA algorithm, and next thing we have to consider is how to plot. So let's do this. Let's say total rewards, numpy zeros and games, and then come down here and say total rewards I equals score. There we go. So that will tally up all the scores from the episode, and we can plot that at the end. So at the end of episodes, plot.plot, total reward, and plot.show. Last thing we have to take into account is the epsilon decrement. So say epsilon equals epsilon minus 2 over n games, epsilon greater than 0.01, else 0.01. And so this will reduce it to 0.01 by halfway through the total number of games, so that we have half the set of games that are taking predominantly exploration type actions, and then half the games taking almost exclusively greedy actions. We don't want to reduce epsilon to 0 because we want to be able to continue to update that model of the environment, which is just the Q function. So I believe that is it. Let's head back to the terminal and try to run that. So here we are on the terminal. Let's go ahead and run this. I did notice there was a syntax error. I forgot a semicolon in one of my for loops, so I went ahead and added that. So let's go ahead and run the Acrobat and see what she does. So it gives us some generic warnings, but it starts to run. So I'm going to go ahead and let that run, and then we will plot the learning so you can see the actual proof that the agent learns. And then I will show you how to save the model so that way you can initiate a sort of testing phase as well. Back in a second. And we're back. So after running 50,000 iterations, 50,000 episodes, that is, I came to the conclusion that's not enough. And that makes sense if you think about it. So the state space is 10 to the 6 states. You've got 3 actions, so 3 by 10 to the 6. Only 50,000 iterations isn't going to give you good coverage of your state action space. So I went ahead and let it rerun for something like 500,000. And you can see here in the console, the output of that is every 1,000 episodes or so, it ends up with a reward of around -80 to -100. So 80 to 100 steps to complete the task. So you take a look at the plot for the learning, and you can see that the agent starts out precisely as you would expect. It ends up doing quite poorly at the beginning with a strong upward slope that plateaus around 250,000 games. Recall that we set epsilon to 0.01 about halfway through, and this plateaus around a score of -100. I don't know what solved is considered, but I would say that's at least clear evidence that the agent is learning and the SARSA algorithm is doing its job. We have one last thing to take care of, the prospect of saving the model. So let's head back into the terminal and take care of that now. So we have one final order of business to take care of, and that is the task of saving our models. So let us do that with the module called Pickle. And what Pickle does is it converts Python data structures into byte files, and then it does the inverse operation of loading byte files into Python data structures. So let's create a flag of load and say if load false, then we want to load up the dictionary like so. Otherwise, we want to actually load our model. And you do that by declaring a pickle in file, like so, equals, call it acrobat dot, what do they call it? Acrobat.pkl. And you have to specify the mode, which is read byte. Then you say q equals pickle dot load pickle in. And that's all there is to that. So then what it means is at the beginning of every program, you set this load flag to either true or false, depending on if you want to load the pre-saved model or not. And that will do precisely that using the Pickle module. However, we're not quite done yet. At the end, you want to come down and do the inverse operation and say f equals open acrobat.pkl. And of course, you need a mode for that, and it is write byte. Pickle.dump, q, which is our dictionary we want to save, and f is the file, and then just make sure to close the file. And that is that. That will save and load the file appropriately, so that way you can go ahead and train your model for a little bit of time, save it, come back and train it some more. This is also helpful if you want to train and test the model separately. So I hope this has been helpful. You have gone from absolutely nothing to coding up a SARSA agent to beat the Acrobat environment using nothing but Numpy, Gym, and Matplotlib. Leave a comment down below, share the video if it was helpful, and I look forward to seeing you in the next video.